Hi, this is Michael Pfeifer. This is another episode of the Metal Conversations podcast. In this episode, I will talk about the component design process. This is the second in our series about the component launch formula. In the component launch formula, I discuss various aspects of product design and manufacturing and things after manufacturing, post-production, where materials engineering considerations are important for making sure that we select materials that will work well in the product, develop manufacturing processes that are capable, and then pursue improvements through quality improvement and with supplier quality and manufacturing quality, and also to deal with any problems that might occur with the product, such as failures that might occur. And so in this episode, I will talk about the component design process. So to me, at a high level, the component design process has 5 steps. I know that for product design in general, it's very complicated. There are various phases of product design, and each phase is very complicated. To me, for component design specifically, there are 5 steps. The steps are to identify the component form and design requirements, identify the materials selection criteria based upon the design requirements, then identify the candidate materials, then evaluate the candidate materials, and finally select materials. And in my discussion, I'll be focusing on metals. The overall concept applies to all materials: polymers, ceramics, adhesives, and other materials. So the first step for component design is to identify the component form and the design requirements for the component. Component form refers to the component's size, shape, and various design features in the component. Now, for many products, a product is an iteration of a past product. It could be whether it's from the company that's designing the new product, or it can be based on a competitor's product. But in any case, it's based on a past product. And so there's already some idea of what the component should look like: its size, its shapes, and its dimensions, or its features. Now, the difference between the product that's being worked on and the past product might be differences in performance or reliability, or perhaps differences in size or shape. So there are changes that have to be made to the overall design, and that includes the components in order for the new product being made. So the first step is to take a stab at the component's form, again, the size, shape, and features. Then the next step is, within the identifying the form and design requirements, the next step is to identify the design requirements for that component. This includes performance requirements, such as the loads it might have to carry, that is the mechanical loads, or if it's an electrical device, the current and voltage it might carry. Also, the reliability requirements. Will the component be exposed to corrosion conditions or fatigue conditions, wear, maybe creep if it's high temperature? There are some cases where weight is concerned, so one of the design requirements might be the mass of the component. Also, there might be manufacturing and assembly requirements, how the component will be fabricated, or how it will be joined to other components. And then there are industry standards, government regulations, and sustainability requirements, and other requirements that are important and that apply to the component that have to be taken into consideration. And finally, there's the cost. How much do you want the component to cost? So all these design requirements, making a list of all these requirements and getting hard data about these requirements is important, because the next step is to identify materials that will work in the component, and identifying the materials requires understanding the design requirements for the component. So the next step, step 2, is to identify the materials selection criteria based on the component design requirements. So the component design requirements help us establish the required materials properties for the materials that will be used for the component. So for example, if the component must support a certain mechanical load, then that helps to identify the minimum yield strength for the material that will be used for the component. If there is a weight requirement for the component, then that will help establish the density requirements for the material that will be used in the component. And if the component will be exposed to salt water, then that identifies the corrosion resistance required and helps identify what materials can withstand exposure to those conditions. It's important to identify the material selection criteria as early as possible during the design process, because we want to determine whether materials options exist. If it turns out that there's very harsh performance requirements or reliability requirements, then we may find out that there are no materials that work out, or that any materials that might work for that application are very expensive. So getting the information as early as possible about the design requirements is important for establishing the material selection criteria. Also, missing information about the design requirements then leads to missing information about the materials selection criteria, and that poses risks to meeting the design schedule, because then the design team will be forced to consider materials that may or may not work in the application once you find out the specific performance or reliability requirements or any other requirements. For example, if the design team is uncertain about the reliability requirements, then you may be forced to consider materials that have reliability that's more than what the worst case scenario, or that are equivalent to the worst case scenario that you think will be encountered during use, and that could result in considering expensive materials. And if you don't consider materials that are for the worst case scenario, then that can pose problems later in the design process if you end up selecting materials that end up not working and end up with product test failures because the materials degrade too much during use and the components fail. So getting all of the design requirements as early as possible is important in order to be able to identify the material selection criteria. The next step after we have the material selection criteria is to identify candidate materials. So we use the selection criteria to help rule out materials that won't satisfy the selection criteria, and then focus in on the materials that we can use. And sometimes it requires using a base metal with a coating over the metal. For example, the base material provides the strength needed for the application, and the coating can provide corrosion resistance. When considering materials, it's important not to rely on their nominal properties values. It's important to consider the full range of values that a material might have for strength or electrical conductivity, because over the life of the production of the product, you can be sure that you will get components and metals that will be at the high end and the low end of the range of values for the specified material. After identifying the candidate materials, the next step is to evaluate them to determine whether they really do satisfy all the selection criteria. There are many cases where there's not complete information about the materials available to know whether they're suitable for sure for the application. Now, usually we can get information about the properties of the material, strength and ductility, or its electrical properties. But often we don't have information about the specific reliability capabilities of the material as it will be used in the application of interest. So we may identify that a material has good corrosion resistance, but it still might have to be evaluated for the particular application being considered. So we can do evaluations for corrosion resistance or fatigue resistance or wear resistance for the particular application. And it's possible to, during the evaluations, we can evaluate more than one material at one time, and that's the beauty about looking at materials or doing evaluations on a materials level. We can evaluate more than one material at one time and be able to consider more than one material in parallel, so that when the testing is completed, we can have data on different materials and see how the data stacks up for the different materials for the particular application, and then be able to make a decision based on which material offers the the optimum properties and cost. In addition to looking at performance and reliability, we also want to make sure that the materials have good ease of fabrication for fabricating components out of the material and joining if you're going to be soldering or welding the component to other components. So evaluating ease of fabrication and joining is important. And then finally, you want to evaluate whether the material is readily available. We don't want to select materials that are difficult to source. Maybe there's only one supplier for the material, or one company is capable of fabricating the component, because that's a problem from a supply chain perspective and could pose problems for cost as well. So again, we can perform all the evaluations in parallel with other engineering efforts, and when it comes time to finalize the design, provide data for different materials and be able to assess which material provides the optimum properties at the lowest possible cost. And then finally, we select the materials based on the evaluations and the testing that's been done on the materials. As I mentioned earlier, there are risks during product design and during component design. At the beginning of the process, we don't have all the information we need to make a clear decision, and hopefully a decision that we believe gives very good likelihood of passing product testing and enabling good manufacturing quality. And as the design process proceeds, we get more information. Ideally, the more information we have about how the component is being used and the conditions to which we'll be exposed to, if we get that information as early as possible in the design process, then that helps with the materials evaluation and selection process, and helps ensure being able to pass product testing the first time and meeting product launch schedules. So the benefits of using the process that I've outlined is having fewer surprises and passing product testing the first time, because we've identified materials that have a high likelihood of meeting the performance and reliability conditions. We develop designs that are easy to fabricate because we're selecting materials that have good ease of fabrication. And that's going to result in lower cost and improved supplier quality. When components are designed that are made of materials that are a hassle to use for fabrication, then that's passed on to you, to the component designer or the company, in terms of higher cost, because the people making that component are going to pass on the hassles associated with making that component. And finally, the final benefit is the improved likelihood of meeting the launch schedule with less stress, because we're collecting information about the materials and the component's design in a methodical fashion, and having fewer surprises as we go along. So the takeaways is that there is a systemic process, or I should say a systematic process, for identifying materials to use in components that helps with component design and doing component design and product development with lower stress, and being able to meet schedules and being able to meet cost targets. So that's it. I hope that you've learned something from this and found it to be helpful. If you have any questions, feel free to call or email. My email address is mike@imetllc. Thanks again for listening, and good luck with your metals. Bye.